Hey, welcome! Ever stop and think about the invisible world of sound that is literally all around us all the time? I mean, from a tiny whisper to a massive concert, it's all run by some surprisingly simple physics. So let's just dive right in and explore the science behind every single sound you've ever heard. Seriously, think about that for a second. Your vocal cords move just a tiny bit and poof, that energy travels through the air and somehow lands in someone else's ear as a clear, understandable word. How on earth does that happen? Well, that's the big mystery we're going to solve right now. So here's the plan. We're going to start with how sound is born, with vibration. Then we'll see how it rides on a wave, figure out what kind of wave it is, and then decode why sounds are so different from each other. And we'll finish up by looking at how we actually use its ability to bounce around. Let's go!
First things first, the origin story. Every sound in the universe, I don't care how big or how small, starts in the exact same way. It all begins with a vibration.
And that's really the key. Sound isn't just a thing we hear, it's a form of energy. And that energy only gets created when an object moves back and forth really fast. In other words, when it vibrates. No vibration, no sound. It's as simple as that. And you see this everywhere. A guitar plays a note, that's the string vibrating. You hear a drum, the drum's skin is vibrating. Even with a flute, the sound comes from the column of air inside it vibrating. You can even feel it yourself. Go ahead, put your fingers on your throat and say something. See? Your vocal cords are vibrating. The main takeaway here is sound and vibration are totally inseparable. Okay, so we've got this vibrational energy. Awesome. But how does it get from, say, the guitar string all the way over to your ear? Well, it travels in the form of a wave. Let's dig into how that actually works. Now, the trick to understanding this is that last part, without the actual movement of particles. Just picture a long line of dominoes. You tip the first one over, and that wave of falling dominoes goes all the way to the end, right? But each domino itself doesn't travel down the line. It just falls where it is. Sound waves do the exact same thing. They pass energy through the air by bumping particles into each other, but the particles themselves pretty much just stay put. Now, to get a little more specific, we need to realize that not all waves are created equal. Sound waves have a very specific identity, and we can figure out what it is by asking two really important questions. First question, does it need stuff to travel through? For sound waves, the answer is a big yes. They're mechanical waves, which means they absolutely have to have particles, a solid, a liquid, a gas, something, to pass their energy along. This is totally different from something like light, which is an electromagnetic wave and can zoom right through the empty vacuum of space. And that, of course, is exactly why, in space, no one can hear you scream. Second question, how do the particles actually move? Well, light waves are transverse, meaning the particles jiggle up and down while the wave moves forward. But sound waves are longitudinal. This means the particles move back and forth, in the same direction the energy is traveling. The absolute best way to picture this is a slinky. You push one end, and you see that pulse of bunched-up coils shoot all the way down its length. That's a longitudinal wave. So this back-and-forth slinky motion creates these pulses of high and low pressure in whatever the sound is traveling through, and these pulses have names. The high-pressure spots, where the vibrating object has pushed all the air particles together, are called compressions. That's the bunched-up part of the slinky. And the low-pressure spots are called rarefactions. This is where the vibrating thing has moved back, leaving a little area where the air particles are all spread out. That's the stretched-out part of the slinky. So really, sound is just a traveling pattern of compression, rarefaction, all the way to your ear.
So if all sounds are just these pressure waves, then why does a violin sound so different from a big bass drum? It's because our brains are amazing decoders, and they're paying attention to three different properties of these waves.
It all comes down to these three things. Any sound you've ever heard can be defined by its loudness, its pitch, and its unique quality, which is also called timbre. And each one of these lines up with a physical property of the sound wave itself. Let's start with loudness. This is all about the wave's amplitude. Think of it as the intensity of those pressure pulses, how much the particles are getting pushed around. A wave with a higher amplitude is carrying more energy, and our brain interprets that as a louder sound. It's basically the physics version of turning up the volume dial. Next up, pitch. This is all about the wave's frequency. That just means how many of those compressions pass by a certain point every second. We measure it in hertz. So a high frequency, where the waves are all packed tightly together, gives us a high-pitched sound, like a whistle. And a low frequency, where the waves are all spread out, gives us a low-pitched sound like a bass drum. Okay, and here's the magic ingredient. The quality, or timbre, of a sound comes from the wave's unique and complex shape.
its waveform. See, a pure note might look like a nice, smooth wave, but the sound from a violin or a person's voice is a messy, complex combination of many waves. And that unique shape is exactly why you can tell a piano and a guitar apart, even if they're playing the exact same note at the exact same loudness.
All right, for our last piece of the puzzle, let's look at one of the coolest behaviors of sound waves, the fact that they can bounce. This whole idea, called reflection, is something we've gotten really good at using to our advantage.
You know, it's a pretty simple idea, really. When a sound wave smacks into a hard surface, like a wall, it just bounces off. We hear this all the time. We call it an echo. But what's really neat is that we can control it.
And this is where it gets so clever. Take a stethoscope. It's basically a masterpiece of sound reflection. That super faint vibration from a heartbeat gets funneled into these hollow tubes. Inside, the sound waves bounce off the walls over and over and over again. All those reflections focus the sound energy, making it much stronger when it finally reaches the doctor's ears.
And this principle is everywhere once you start looking for it. A megaphone uses its cone shape to reflect sound waves forward so they don't spread out and waste energy. And those crazy curved ceilings and panels in a concert hall, they're designed specifically to reflect sound perfectly so that every single seat gets a great experience. We have become experts at telling sound where to go.
All right, so let's tie all this together. We've learned that sound is energy, and it's born from vibrations. It travels through stuff as a longitudinal wave, a series of high and low pressure pulses. And everything we hear, the loudness, the pitch, the quality, is just our brain's interpretation of that wave's physical properties. And of course, we've learned to harness those properties in some really incredible ways. So I'll leave you with one final thought. When you're in another room and you hear a friend or a family member talking, you know who it is instantly, right? You don't even have to think about it. So based on what we've just covered, what property of their sound wave are you actually detecting? It's not just how loud they are, and it's not just how high or low their voice is. It's that unique quality, that waveform, that's as distinct as a fingerprint, isn't it? Pretty cool. Thanks for joining this explainer.